And we'll come back into this. I'm not sure of how best to go through this, so I'm going to kind of rely on your ability to stop me and ask questions as to what the benefit is of going through these things in R. For those who don't play with R, you can pretty much steal this code and adapt it without having a whole bunch of R programming skills. It is its own kind of language all by itself. But here's maybe how you adapt the code that I sent out to you yesterday. R has as its original history programming on a Unix environment, and Unix addresses files, has a slightly different syntax for addressing files than Windows does. So in order to have your program run in a particular directory, you need to set the working directory to something else. And you can paste in the location of what you have. You can either do 2 backslashes or you can do 1 / because / is kind of native. Here are in order to run your programs, you need to call up the libraries. So these are the libraries that I use in this example. The psych library has the factor analysis program in it. ggplot2 is a graphics package. The corrplot is the correlation matrices plot program that I talked about in the handout. GPA rotation is a very general factor rotation program, and the next chapter that we'll talk about gets into factor rotation, so we won't talk a lot about that here. And the N factors library is one that has a lot of tests for the dimensionality of the solution. So what I do here is I read my data in. I have a tab delimited data set. This \t says I'm using tabs, and this is the name of the data set. And header equals true means the first row of that matrix contains the names of the variables. So just for the heck of it, if we come down, we'll read all of that in. And down here is where you can see what you've got going on for your programs. Head is kind of a useful statement that will just show you the first few observations that you have in here. So these are the names of the variables in the data set. I have quite a few here because I use this example quite a bit. NA is R's way of talking about missing data, and that's a little bit frustrating when you're porting things into SAS or M+, because SAS can read things that are a single letter and say, oh, this is a missing data code, but it won't take 2 letters. And M+ will not take characters at all. So you have to kind of fix that before you export those data sets that are in R out to those packages. In order to look at a certain subset of analyses, I'm going to have to tell the program, oh, there's a list of variable names that I want to have. So C is the concatenation operator, and these are the names of the variables separated by commas. So I can run that program, ta-da. And in order to take my original data set, which had all those variables, and limit it to only those variables, I subset, put hard brackets around and say, here's my vars. There's that. And it's frequently a good idea to run some descriptive statistics on your data. I've seen way too many doctoral dissertations over the course of my years here to realize that sometimes the data you're reading in isn't the data that you think you are reading in. And the describe statement works really well for that. That'll tell you, whoops, sorry. That'll tell you the means, the standard deviations, and some summary statistics on this. So I'm doing this to verify that my sample sizes are what I think they are. and that the means are what they think they are, and that the minimum and maximum values are what they think they are. Now, generally speaking, that's 99% of the mistakes that can go wrong in reading data. If you want, you can generate a correlation plot. So that's the name of the data set. I want to see numbers, and I want to put a label on that. And this is a type of a correlation plot.
I have a question.
Sure.
So can you move a little bit upwards for descriptives? So, but on the console, not to the on the main. Like, yes, here. Can you move towards
This?
up on the console?
Yeah.
Yes, here it says trimmed. Can you move backward?
Okay, like this?
Yes, I have a question related to descriptive.
Okay.
Descriptives. If you move a little bit.
Oh, okay. The descriptives, that's down here.
Yes.
Yep. Okay.
So it says trimmed.
Mhm.
What does that mean?
Trimmed means it's throwing out extreme observations and recalculating a mean. So
Oh,
if you start to see that mean changes a lot from the trimmed value, that might tell you that you have some either, well, probably outlying in individuals. Windsorizing, we talked a little bit about. That's the process of taking an extreme value, and instead of taking it at its word, you assign the next highest value. So looking at differences between the mean and the trim sort of tells you if you might want to explore Windsorizing, perhaps.
okay. So if we see some extremes, should we remove these observations before further analysis?
Well, you can. Though the rest of the examples that we'll go through are hopefully going to show us this. So to me, the descriptive statistics are useful for telling me, did I read the data incorrectly? And are there some ideas about maybe what the distributions are that are realizable by a number? But graphically, we're going to see some pictures that will kind of tell us that. So you're the analyst. You're the one who's going to be an expert on the data. The only thing I would say, just as advice that applies to all of the research labs you're in, is never overwrite your original data, because you need to have this thing called an audit trail. You need to be able to go back to your original data as it came in and then show people, and this is how I got to the next step and the next step and the next step. Because, and especially if you're talking about something like at this stage, gee, it maybe looks like I need to make a decision about something, you might want to go back and revisit that. So, I mean, I'm fine with doing the corrections however you do so by your best decisions, but just don't overwrite your data so that you can't go back and undo that decision later on.
Okay. Thank you.
Okay. Anything else, gang?
I have a question.
Yeah.
Yeah, I saw that when you show the head of the data, there are variable names. Why did you add some variable names again?
Well, so let's go back and look at that head again. So this is the first 6 observations in the data set, and there are many, many variables in that data set. So I've got the wave 0 data, the wave 1 data, and the wave 2 data, for example, because I have 2 at the end. And I don't want to factor analyze all my data. I just want to look at a given subset of variables, in this case, the wave 0 variables. So this code is going to tell the computer program what the names are of the variables I want to keep. And this code down here tells me exactly what, now make me a new data set called RFD, for reasons for drinking, based on all RFD data that I just read in up here, and subsetting only the my variables.
Oh, I see. Thank you.
This is my dream that I have questions during class. So if I would have known that walking through code would have questions, I'm very happy. Are there more? So yeah. Okay, so come to think of it, if I open up the chat thing here, I'll just keep that chat box open over here in case someone feels the need as well. So down here, the core.plot statement made this correlation matrix down here that I'm looking at. I can use the zoom statement and make that bigger so that we can all take a look at it. And you'll see that that kind of gives you a plot, a heat map. So on the right-hand side, you have correlations going from -1 to +1. And on the diagonal, of course, you have correlations of 1. And the shading here kind of gives you a visual picture without you having to look at all the numbers as to where the high correlations are. It's not incredibly pretty, but it gets you there. If you want a slightly nicer one that I used in the book, that's the GG corrplot program. So if we call up that library and we do the correlation plot, that's run a correlation of the RFD data set, use pairwise complete observations so that if there's some missing data, but on some variables, I don't throw the people out entirely. I'm using all available data. The order that I want to have is the original, that is the columns that I have in there. And then there are a few other things here that are just housekeeping of the color and the rectangles and so forth that are options. If you ever want inside of R, you can come down here to is it the help statement or the packages statement? You can come down here and find the manual for the visualization of a correlation matrix, and that will give you all of the options that apply and all the parameters that you can have. So if we run that, that generates this picture, which should look vaguely familiar. And it's a little nicer. I don't have numbers. I mean, I can put numbers in the upper diagonal or the upper triangular and dots elsewhere and so forth. But that's the basic graph that I have here. Inside of this picture, you can also use the export statement and then save this as either an image or as a PDF. If you're saving things, just a little lecture about pictures. If you're saving things as a JPEG or a PNG file, that's going to be just a record of pixels for you. And another way of saving your data is called vectorized form, so that a line is considered in the image as starting at a certain place and ending at a certain place and having a certain thickness, and there are also vectorized commands for shading things. If you want to take your picture and then do some more processing on it, like you want to make it look pretty like I do in the book, you'll want to use something like Adobe Illustrator. And if you call that in vectorized form, you can actually click on the elements, the lines, the text, and you can change the fonts and the size of the fonts and move things around. So if you ever want to, those are your options. So SVG and TIFF are vectorized options. Encapsulated PostScript is also a vectorized option, and Adobe Illustrator can read all of those things. JPEGs and PNGs are not. So that's how you can then copy that and paste that into your thesis or dissertation.
I have a question related to these images. So whenever I try to save the image like that, the quality decreases, the image becomes blurry.
Well, what's happening there is I suspect when you're saving it, you might be saving it as a JPEG.
Yes, I was using JPEG or PNG.
And when you'll need to keep track of what the size and the height are, or the resolution of that JPEG. And that's another argument for saving things vectorized, because you'll lose all the blurriness. And you can, again, save that. I believe if you're saving things as a PDF inside the PDF, it's saving it as a JPEG. So, that's kind of my answer in terms of saving things inside of, from R and putting them out. But
Okay, thank you.
right, sure.
So I have another question. It is related to the picture
Mhm.
here. So when we look at the graph or figure, should we only accept the factors on the diagonals, or we see some square patterns, other exact diagonal
So
squares?
on this, so your question is, what are we always going to see ones on the diagonal?
No, my question is, so we see patterns here, the square patterns, like it is 5 by 5, like
Mhm.
patterns. So my question is, do we accept these as like each of these big squares as one factor, indicating one factor?
Yeah. That you might
And
think
this,
about that as one
yes,
factor. Yeah.
one factor, and then the other. So this was one of my questions. The other question is, so I see two other big squares
Mhm.
that's placed other than diagonals.
Yeah.
One is yes there, and the other one is just the opposite of this.
Right.
Yes. So should we also accept this as another factor, even though they are not on the diagonal?
Well, this is a good class discussion topic. So here I'm looking at this picture, and you're right in saying probably there's some evidence for there being 4 factors because I see 4 squares on the diagonal. And then I see this off diagonal correlation, and I see that there's a big square between everything that could be factor 1 and everything that could be factor 3. And then these other squares over here, they're kind of a lighter blue. So based on this, I might say maybe there's a 3-factor solution, and the 3 factors are all correlated with each other. And those 3 factors have nothing to do at all with this factor over here, which is related to how alcohol tastes. That's one possibility. Another possibility you might say is maybe there's a general factor here, a hierarchical factor, and these little items down here that are on the diagonal represent clusters of unique items that are little subfactors. So, or maybe it's a bifactor model. So based on looking at this, the 3 things that would happen in my head are to think, I want to look at a 4-factor solution and probably look at it as oblique, and I'm probably going to see some correlations going on with 1, 2, and 3. I might do a hierarchical factor where there's a general factor that predicts factor 1 and factor 2 and factor 3, and then subfactors where these items define factor 1, these items define factor 2, these items define factor 3. Or there's a great big factor, and in addition, there's 3 little baby factors. So just looking at my picture, those are the things I'd come away thinking. But I would know down here, this taste factor has nothing to do probably with what's going on with the other 3.
Okay, thank you.
Sure. Okay. The next thing is to do the core plot again, but now I want to hierarchically cluster it. So the only thing that's different is instead of original, which is the order that the variables are on the data set, I want to cluster this. And that gives me, excuse me, I keep running the wrong thing. That gives me this picture. And all it has done now is to order the variables so that I can now see that was factor 1 and factor 3 are sitting next to each other, and factor 2 is moved over here. I mean, it just rearranges things. And I realize in this particular situation, that's maybe not particularly enlightening, but if you have a survey and there's all kinds of items and it's a big jumble of correlations, it's a little nicer to be able to have that organization for you. It helps you think about what's what. So I might want to do some more explorations of the correlation plots with the spline regressions and the summary statistics. And those particular plots get to be really big, and I couldn't fit them into the book. So what I'm doing here is to consider just the items from a particular survey. So I'm going to make a short variable list of just those variables. And I'm going to say, make me a data set called short list based on all of my data. And I might want to look at the correlation matrix that results and do a factor analysis. So if I'm factoring these variables, the name of the program is FA. The correlation matrix I'm putting in is the correlation matrix that I generated. This diagonal is going to have squared multiple correlations on it. And the factors that I wish to extract are 5, and I don't want to rotate anything. And PA is my principal axis factoring. So that's going to run. It says there's a Haywood case. I can talk to you about that in a moment as to what that is. After I've run FA, I can then print out my factor loadings. Well, the way that R works is when you run this factor model, it creates a data set listed on the upper right-hand corner here that's going to show all of the results of my factor analysis. And one of the elements of that are my factor loadings. So what this is doing is say print my all 8 factors that I just made in my factor analysis, and the thing inside that I want to print is the loadings. Give me 2 digits of precision, and the cutoff value is minus 0.5 for the loadings, and that's going to give me this thing. So here I see my factor analysis for my 5 loadings. This is an unrotated solution, so this first factor is a big one. It's all of the correlations that I have in the data. The second factor is half positive and negative. And the third factor is half positive and negative of that. So for example, these first 4 ones were negative. In factor 3, first 2 are positive, the next 2 are negative. And this pattern of positive and negative loadings arises because, as we talked about in the last lecture, of the way that we extract factors, that the first factor gets a crack at the entire correlation matrix, and the second factor is defined based on the residuals after adjusting for that first factor. If I want to use, that's just a brief little sip of what the factor analysis program looks like, and I'll talk more about rotating and other options later. If you want to have the panel correlations going on, this is based on my short list. I want to jiggle the numbers so that, because the scale items are 1, 2, 3, and 4, so I kind of want to move those dots around to get an idea of where the data are. And when I do that, that takes a little bit of time to cook, even on my computer. I should be getting a printout here. There we go. And, this is the printout that you see in the book. It's kind of graphically intensive, but, on the diagonal, you have the univariate histograms of the data. In the upper diagonal, you have the values for the correlation coefficients. And down here, you have the scatter plots with the little red lines. Let's make it bigger. The little, takes a while to show this thing. The little red lines are the lowest regressions, and the ellipse is an envelope that should incorporate 95% of the data. I believe it's 95%. I have to check the manual. and the little dot is the median. So, okay, now I can X out of that. Good. And, similarly, I can make a really short list and do the same thing there for just a certain number of items if I only wanted to look at what the relationships were for the items inside one value. And the reason that I do that is, again, so I can have a more graphic look at where my data are, and you'll see those jitter values give me an idea of how many data points I have out there. So I realize this is, kind of a fast introduction, but I'm hoping that you can steal this for your own work. If you're going to do a factor analysis with parallel factor analysis, I can't do a parallel analysis if I have missing data. So I will either need to impute a data set where missing data are replaced by something, or in this case, I'll just throw out observations with missing data. So what this is doing is it's taking the reasons for drinking data set that I had and omitting all those observations that have NA for not a number.
I have a question. Which one is more robust, omitting the data or imputing the data?
Missing data is a huge issue. We could have a whole class on missing data models. But just to give a fingernail sketch of imputation, inside of, say, Onyx, we saw that you could read your data in and you could automatically randomly impute data. Other strategies for imputation involve looking at your data and making an observation and making a guess for what that individual should answer based on that. So, if it's a really bad idea, for example, to say, if a person has missing data on an item, I will substitute the mean in, because people who have missing data could be systematically higher or lower. Some people also substitute the mean for a group. So I might substitute the mean of all 7-year-old males for a 7-year-old male who happens to have a missing data point. And those strategies tend to reduce the amount of variance inside of a group. So there are various ways of imputing. Amos has a really nice stochastic regression approach to making an imputed data set. And inside of R, there are also some imputation strategies. And the thinking here is, I'm going to replace a missing data point with a data point that both is representative of what that person should have answered, but also contains a certain amount of random error in it so that the variance for the variable is not affected. And that's generally a better way of doing things. In this particular, in this particular analytic example, though, all I'm interested in doing in my parallel factor analysis is deciding on dimensionality. And given that I don't need to worry about missing data if I'm fitting my confirmatory factor model, or if I'm doing my exploratory factor analysis itself, I opted in this case just to do an analysis based on complete people, hoping that I'm not doing great violence by doing so. If it's the case that people who have missing data actually represent a qualitatively different group of people, well, that's kind of a big problem. But that's it's a fancy way of me to say this is a complicated issue, and there are no single right answers. But in terms of an analyst, this is the reason why I decided to run the model just based on complete observations. And you could argue with that. If you were a reviewer of my paper, you could say, I don't like this, do it a different way. I'd have to do it a different way. So if we're doing a parallel factor analysis, I'm going to call the FA parallel program based on my data set of complete observations. And these options are a little bit specific to factor analysis. The method of extraction is minimum residuals, and that's the factor analysis that we want to do because we're factoring residual matrices and so forth. So I can run that. And what that's going to do while that's cooking is it's going to iterate to 100 times. It's going to give me error bars around my parallel factor analysis. And I can come upstairs here and look at my picture. And this is what we see in the book. Here's my, let me move the chat window out here. I have factor analyses and I have component analyses. So the component analyses are having ones on the diagonal, and the factor analyses are having squared multiple correlations. So the first thing that stands out for you, as I mentioned before, is when you're doing your component analysis right here, that gives me pretty much the same scree plot picture as when I have the factor analysis. And the reason that the factor analysis eigenvalues are always lower is because I have squared multiple correlations on the diagonal. I don't have as much variance. But this picture in practice is going to look very similar. It's just that you'll notice when you do FA, when you're doing a factor analysis, you can start to have eigenvalues that are negative because you're extracting more variance from the data than there is variance actually present. And the two techniques, so in terms of the Zhang and Lim psych methods paper, if you're doing a parallel factor analysis, you should really be looking at the PC solution and not the FA solution. And the two approaches here are to generate a simulated data set based on the correlation matrix and to do a resampling of the data based on a random permutation. And in this case, we're having pretty much the same thing in those data sets. Those two lines actually overlap quite a bit. And the reason that these lines overlap quite a bit and the reason it's so darn flat is because we have a very large data set. We have a couple thousand observations here. All right. And just using that component is exactly the object of the second set of analyses that I have here. Eigenboot Parallel is another program inside of R that will do parallel factor analysis as well. So if we're going to repeat the picture that we just saw, if I'm doing the model for factors, I'm going to show the 95% confidence interval around this. I'm going to do 100 bootstrap samples of the data. I'm going to permute the data around the way that I described for Horn's analysis. Again, this is for factors, and parallel factor analysis wasn't built for factors, but you can do it.
I have a question.
Sure.
So what is the default for number of boots? If we don't specify for 100, what is the default?
Permute parallel. Well, I don't know. Let me come and look. Eigenboot parallel. I might have to update my list here. Sorry about that. It would be in the manual. Well, it would be in the manual. I mean,
That's okay. I can check
yeah,
that.
yeah, you can
Thank
check
you.
that. I don't want to restart the session and have it
Mhm.
reload and so forth. And did I have my model? Yeah, that's giving me more or less the same thing. And for the second model, it will also run and give me the components. And then what I do is I take the parameter values out of those eigenboot parallels, and I'm going to concatenate the factor analysis values, the principal component values, and so forth, all from these two models that I made. And that will give me, where's my par values? That gives me the same numbers that I have here. And I can then export that to a graphics thing and make a picture as well. I mean, it's absolutely the same thing. And then if I wanted, I can take that data set and write that out to an Excel spreadsheet as I show here. And this section in here, we can kind of gloss over, but this is taking the first 200 observations and rerunning the same thing to show you that when I do the analysis, I'm going to get that slightly higher value for the plots down here. You know, these are not all absolutely flat now. There's a little bit more of a falling away that happens because I'm looking at a smaller data set. And that's, as I talked about in the chapter, in practice, if you're only doing a few hundred observations, you will start to see these eigenvalues decrease, you know, be larger at the beginning and decrease. So the moral of the story, folks, is in things like SAS, SPSS, and R, when you do a factor analysis and you use the Kaiser criterion, that is, if you say, I'm going to factor all eigenvalues greater than 1, if you had random data, you will have a number of eigenvalues that are greater than 1, even if the data are completely random, if it's purely trash. So, you know, I make this point that you should not use the eigenvalue greater than 1 criterion, even though it's a default that many programs will use. If you're in, I talked about the scree test, and remember that the scree test, well, we have a little picture right here, involves making a regression line based on the first two and seeing if that regression line is different than the third, adding a regression line based on the first three, and continuing that process in an effort to find an elbow. So if we're doing that based on our principal component factors, the results of the Cattell test suggest that I have a 3-factor solution here. So the NCNG program is what will do the Gorsuch test. And I wrote that into a little thing called results, and I printed that results out, and I got the number 3 down here. That's based on the principal component values. If I want to do the factor analysis values, it's the same thing. Again, I also get the number 3. If I want to do the Velicer Map Test, that's VSS. And here's the results of that. So, you know, that's telling me I've got either 2 or 3 factors based on VSS complexity. The Velicer Map Test tells me I've got 4 factors. And that's kind of nice because that kind of squared with what our eyes were telling us when we looked at the corrplot. In addition to the number of factors, you do get traditional fit measures. So if we come down here and look at 4, the RMSEA is 069. That's not great. The BIC and the adjusted BIC are these values. Lower is always better. So, you know, If you were looking at only the BIC, you'd say you have 6 factors. These other ones, frankly, I do not know and I do not use them. But over here you have your chi-squares for the models and the p-values associated with those and the degrees of freedom for those various models. So that's how you get your Velicer Map Test out. If I want, I can make a correlation matrix of the reasons for drinking data set, and I can use that based on the pairwise complete observations, and I can request Pearson correlations. I'm making this data set because I'm going to do some factor analyses. And I can look at the correlation matrix that I made. It has ones on the diagonal, that's nice. And off diagonal, I have 1 digit of correlations. And I can also produce the statistical significance levels of all of those correlations by the corrpmat function. And if I want, I can then take my correlation matrix and make a GG corrplot of that, which looks like this. And so that's just another version of a heat map. I'm not particularly in love with the ordering of the variables. I guess I would much rather have my ones be from the upper left to the lower right, but you can fix that by reordering the variables. I can also look at just the lower triangle of the data. And that's a little bit nicer. And it also gives me a little bit of a heat map. So, those are just other options that are out there. And, this is where I'll take us through here and do this first analysis. If I'm, excuse me, you can go find, he likes to complain about the squirrels outside. You can do a factor analysis for the reasons for drinking data set, extract 4 factors and select no rotation and do a principal axis solution. There. And then I can take a look at the results of that, and that will give me the factor loadings. You make this bigger so we can all see it. That will give me the unrotated factor loadings for this solution. First factor, second factor, third, fourth. H squared is my communality. So this is an orthogonal solution. So that 0.72 is equal to the sum of the square of 73 squared, 27 squared, 23 squared, 25 squared. The uniqueness is 1 minus the communality. So 1 minus 72 is 28. And the factor complexity is a number. I mean, we don't talk about it much, but it's how much items tend to cross-load in this solution. But it's not a number that we really use that much. The sum of the squared loadings for factor 1 is 7.93. That's all of the numbers in the first column squared and added up. Same thing for factor 2, factor 3, factor 4. Because this is an unrotated solution, these numbers have to strictly decrease over the course of time, over the course of the number of factors. And the proportion of variance in the data accounted for by the factors is the total variance of that variable added up, and being the denominator and the proportion of variance explained by that factor across all the variables. So this is a kind of a measure of R square. And the cumulative variance is the sum of how much variance you've explained so far. So 40 plus 0.16 gives me 0.56, 40, 0.16, and 0.09 gives me 65, and so forth. So at the end of the day, I've explained 69% of the variance across all my variables with my factors. And if I'm testing my model, I get a chi-square out and a root mean square residual. Just the standard model fits for this structural equation model that is an exploratory factor model. The bit about the harmonic number of observations and so forth well, it's a guess as to what the chi-square would be with its p-values, so it's significant. But again, I have a lot of observations, so I'm probably going to get a significant chi-square. The Tucker-Lewis index of replicability, I'll talk about later. It's basically a measure of would I get the same factors out if I redid my study. And the RMSEA and BIC we've talked about before. So, that gets us a start in R. If you're playing with SAS, I've talked to you a little bit about this, and this gets us into the next topic, the last topic for the chapter, which is iterated components. So here inside of SAS is a factor analysis done just the way we always know they are. I first off factor the correlation matrix. I have ones on the diagonal, and this gives me this eigenvalue, these eigenvalues, and this eigenvalue by dimension plot. It's the same thing we just saw in R. And the factor pattern consists of the loadings. And this is an unrotated solution. So again, this first factor is going to be the biggest loadings, and the next ones are positive and negatives and smaller. Well, down here, I have my final communality estimates. So this 0.5758 is equal to 0.62 squared, 0.97 squared, 40 squared, 0.8 squared, 0.1 squared, and 0.3 squared. That's how I have that communality estimate. And notice that as I ran this, I didn't say anything about how many factors to extract. So it took all the factors that were bigger than 1, which is how I ended up with 6 factors. And we saw in the analysis and in the plot we're looking at, 4 is probably a better number. So based on the scree, I should, if I'm doing a thorough job, I should explore 3, 4, and 5 as the factor solutions to entertain and think about, does this mean something? So let's say n equals 4, and that will give me a 4-factor solution. All right, and we have a 4-factor solution here. Now, usually, there's somebody in the class. In the before times when I could talk to people, I had this sort of Socratic way of walking people through, maybe we want to improve my factor model. Because upstairs here, we had this belief that we were factoring a correlation matrix. Communality estimates were 1. And then we did all of this magic of extracting factors, and we ended up with this factor pattern here. And there were loadings here. And down at the bottom, I had these final communality estimates, which is the sum of the squares of all of these loadings. Well, why don't I go back then and take these numbers and put those on the diagonal and factor the model again? Well, that's going to result in a different set of factor loadings because I'm factoring a different model. And at the end of the day, I'd get another set of communality estimates there. Well, one of the fun things about statistics is, if you don't know an answer, it's a bit like Alice in Wonderland's Tweedledee and Tweedledum. If you'd ask Tweedledee a question, he'd say, well, if you ask Tweedledum this question, I'll tell you. And you ask Tweedledum the question, well, Tweedledee has the answer. There's this looping back and forth between two things I don't know, which is really one of the, and coming up with an answer. Well, that's what iterated principal factors is. So instead of prin, let me say prin IT for iterated factors. And the reason I'm doing SAS is SAS shows you what's going on in that model. So let's come in and take a look at this. Iterated factors starts out with ones on the diagonal and gives me a scree plot and then factors that and gives me all of my communality estimates. So this 0.574 is the communality we had for the first variable in that printout we just got done looking at. But then we take that 0.754 and we come upstairs and we stick it back on the diagonal of the correlation matrix and we recalculate our factor model. And after I do that, the communality goes down a little bit. Some of them, go down by quite a lot. And I'm going to keep doing this process until these numbers, in terms of the communality, don't change much at all. And that's all there is to iterated principal components or iterated principal factors. In this case, I'm doing iterated principal components because I started out with one. If I'd start out with squared multiple correlations, I would have iterated principal factors. In theory, you should end up with the same communality estimates regardless. But this number down here, this 5.2, is an arguably much better number for the communality than what I had in iteration 1. So iterated principal factors is actually preferable to just doing a straight factor analysis. Well, now that I have these numbers here, I can come back and recalculate my eigenvalue by dimensions plot. And hopefully, if God is in her heaven, I'll have a scree plot that's going to also show that preference for a 4-factor solution. Well, it kind of does. 8, 1.6, 1.3, 0.9. Those kind of look like big numbers. And then there's this sharp drop off to 0.5, 0.37, and so forth. And again, just as with squared multiple correlations, because I don't have ones on the diagonal, after a while, these eigenvalues are going to go negative. But what I'm doing by looking at these numbers is to try to figure out, what is the number of dimensions present in the data based on the picture? And down here at the end, I have my iterated principal factor solution final estimates. So at the end of the day, I have an unrotated solution of 0.608. Well, that's a little bit different than what I had before, which was 0.626. In theory, your numbers should be cleaner. These numbers should be better and more believable. Oh, can you hold on just a second? Hello. This is Phil. Excuse me. Are you outside my door? Okay, come on up. I'll be with you in just a second. I'm finishing my class. Okay? Sorry about that. I found somebody's credit card and wanted to return it to them. So these numbers should be better based on the idea behind what an exploratory factor analysis is. So I see that I'm at time. I'll